Ram Shankar, shall we get started?
Yes, Professor, please. Yeah.
Okay, I was waiting for you, so I thought you will tell
No,
me.
I was just waiting. Yesterday we had some good numbers. We see a drop today. Please start. You get started, Professor.
Yeah, okay. So
Thank
I
you.
received
This
one
meeting is
message
being
from Soumya
recorded.
that we have to disable some annotation or something.
Soumya, can you please guide him?
Oh, yes, sir, sure. Sir, once you share the screen,
Yeah.
you will
Yeah.
you can see the more options. So we can just disable the
I have
annotations.
disabled. I have disabled.
Okay, sir. Thank you.
Yeah. So my screen is shared. I think you are able to see my screen, right?
Yes, sir.
Yes, Professor.
Okay. Should I switch on my video or shall I keep it off?
It's your wish. We can get started.
Yeah. Okay. Okay. So
Thank you.
I'll.
Please go ahead.
Yeah. Okay. All right. So thank you everyone for joining this session and welcome to this session. I am Professor Abhishek Dikshit from IIT Delhi, Department of Electrical Engineering. So I gave a talk previously in this forum, I think a couple of months ago. That time we were talking about cryogenic CMOS as a sort of, offshoot of the regular CMOS and what kind of performance we can expect from CMOS at cryogenic temperatures. In the same series, this today's talk is more advanced, along with the mission, we are all also, learning newer things and, expanding our horizons. So I'm just trying to, get you the updates as we have them. So today we'll talk about more advanced topic. So we'll go towards a large number of qubit-based quantum processing unit using semiconductor qubits. Why is it not changing? So first of all, few observations, and my opinion. So I think the first point everybody will agree with that, currently we are all witnessing a revolution of sorts. And there is both a lot of excitement in the market as well as sometimes adverse impact on jobs and so on because of AI and other technologies at play. So what I expect is that in near future, if you have the required compute power, for instance, NVIDIA GPUs, in those countries, you will further grow AI and AI-based, applications. But if you are restricted in that, which is what is happening in some countries where these GPUs are getting restricted to sort of contain the AI growth. But in longer terms, there will be a time when GPU scaling will saturate, and that's where the quantum computing is likely to kick in and become the next big thing in terms of driving the technology revolution further. So that places the quantum computing in the right kind of place in terms of the importance and the relevance. There are, of course, lots of caveats to this. For instance, we can say that quantum computing is useful only for certain kind of operations, right? But whenever we talk about this, we are really looking at a QPU as an accelerator, just like a GPU is an accelerator for certain kind of things. So overall, in terms of a compute infrastructure, we are looking at combinations of CPUs, GPUs, and QPUs. And we anticipate that the kind of, punch that a QPU will bring to the overall computing scenario is going to be massive in not even 10 years, maybe slightly earlier than that in times to come. Here is the outline of my talk. So I briefly wanted to talk about quantum computing just for the people who are completely new to this area as I am. What quantum computing is, we'll just look at a simple example to understand what quantum computing is and what it is not. And then we'll talk about a little bit of device technology, not much of a device physics, in terms of the kind of qubits we plan to work with. And then I go into the slightly, main topic of this talk, where we'll talk about QPU design, implementation, and how we design using this 1D tile. And then I'll try to summarize. So I only have 1 hour, so I'll probably run through the slides at a faster pace. So let's talk about quantum computing in a nutshell. So I just want to say what is different between classical and quantum computing. So if we are all familiar with classical computing, right, the current computers. So if you talk about a bit X, it can have logical states 0 or high, 0 or 1, either low or high. Well, in qubits, we can call a similar thing like a possible energy state, right? So logic states typically are identified with voltage levels. Here we are talking about energy states, calling +1 as low or -1 as high. And very important, the relation between the qubit state and bit state, x equal to 1 minus z by 2, right? So if you put, for instance, z equal to -1, which is corresponding to high, you will get x equal to +1, which is high for the classical bit. So now, unlike the logic gates, for instance, and or, in quantum computing, what you do is you take two qubits, q0 and q1, and you allow them to interact, right? And you can kind of create this kind of a equivalent of a truth table of sorts, right? So when both qubits are in low energy state, you of course get your system energy lowest. When both are high, you get it highest. Otherwise, you get some intermediate energy, right? What you really want from your AND type truth table is that in these three states, it should give you a low, and only in this state it should give you a high. That would be the correct truth table for a logical AND. Now, what we try to do is we try to encourage certain results, and we try to discourage certain other results. So think of it like a interference, right? So there is a constructive and destructive interference. So that's the kind of methodology we apply in a quantum computer. So that the states which are going towards the lowest energy, those will actually get encouraged, and the ones which are going towards the higher energies, they are not going to get encouraged, and they will be basically destructively interfered. So it is easier to understand it from an example, and we take an example which is kind of common for ECE and computer science people. So if you go in electronic design automation, this is a classical placement problem. So you have 3 cells ABC, and you have to place them in 3 sites or 3 locations, 1, 2, 3, such that every site has a cell, and then there is the shortest wiring distance between these ordered cells like A to B and B to C. So that's the problem. Now, computer of course doesn't know spatially what we are asking for, so you only have yes and no questions. So questions will be like, is cell A in site 1, is cell B in site 2, is cell C in site 3, and like this there will be in total I guess 9 questions, right? So each question will have only one of the 2 answers, yes or no, and these are the only things that we can encode. So you create a table of switches, something like a flip-flop. So 9 switches in total for this problem, and these are your switches, right? And for every cell there will be only one on statement, right? So every cell is supposed to be only one of these sites. Now we take this kind of a situation where A is in S1, B is in S1, C is in S3. Now this is an illegal placement because A and B both are in the same site, which is not allowed, right? So one site S2 is empty. So now you tell the computer, look, this placement is bad. Why it is bad? Because of this, and it should be heavily penalized. So you basically code some kind of a error, right? Error-like thing, and eventually the energy of this solution seen by the computer will be very, very high. Okay, so this is something like a DRC errors you will encounter in layouts and so on. If you get such a placement S1, S2, S3, everything is correct. A to B distance is the smallest, B to C distance is smallest. This is a good placement. So this is basically a low energy, right? Low cost, low energy cost. Instead, if you get this kind of a placement, now you see there is a wiring error because the wiring between S1 and S3 is not minimum. It is two units, right? Whereas it should have been 1 unit between this, 1 unit between this. So now again, it is a bad placement. So you basically declare a high cost for this. Now, we don't basically tell the computer to choose the best placement. We just say that every placement has an energy. illegal placement, very high energy, long wires, slightly lower but still higher energy. Short wires is the lowest energy. So these are similar things we have done, in EDA before, like for RC delay and power dissipation, routing, congestion. These are the things we do while we look at the placement. So now the quantum computer does not understand cells or wires, does not understand placement. It only understands qubits and energy. So now you attach an energy number to every possible switch configuration, like 2, 3, I have shown possible situations. And now you ask the system just to find the lowest energy configuration. And you add these 9 switches. So each qubit represents one yes and no question. So now you will have 9 qubits like this, Q0 all the way up to Q8, each representing a switch, right? And qubit measurement will give you the answer. If it's a 0, it's a no. If it's a 1, it's a yes, right? So you put all the qubits, first of all, in a maybe yes, maybe no superposition state. You apply interactions. You let the qubits interact. You penalize illegal overlaps. You penalize long wires, right? Rest of the work the physics will do. It will reshape the probabilities, measure the outcomes. So you don't get one single answer. You rather get like these placements are appearing most often, which are of course the lower energy ones, and the higher energy ones will appear less often. And the most frequent ones are the lowest energy placements. That's the kind of expectation value based outcome you are going to get from a quantum computer. So in a nutshell, that is how computing on quantum computer is both similar and different from classical computers. Of course, there are many problems. If you are interested, you can find it even online, traveling salesman problem, Alice and Bob problem. There is lots of problems defined like this to give you, understanding of this problem further. But I think this is a good enough introduction to tell us both that it is not very different from classical computing. At the same time, it is not much similar to classical computing either. Where we are in terms of quantum computer design, so our layout for our quantum computer is something we have worked on. I am showing all the component level things that my technical group led by IIT Delhi is working on. So all of these areas we are working on. So at the top you have the job scheduler, transpiler, and visualization, which is all happening on classical computer, basically a CPU. And then you have the benchtop electronics, you have RF SOC, FPGA, you have control is distributed across different temperatures. So this is room temperature control, 4K control, 100 millikelvin control, and control is going, some part of it is even going to 10 millikelvin, and then you have the qubit chip. So we have a large team, different people are working on different things, but it's a pretty challenging overall thing to do. So that's why we require a long time to achieve this. Now in this section, I want to talk about how we take qubits from physics to systems. The focus of my technical group is not so much on fabrication of qubits or fabrication of devices. Our focus is more on designing the system with the available devices. So there are primarily, when we talk about semiconducting qubits, you can use a qubit in 2 ways. Either you can make it like a charge-based qubit or make it a spin qubit. Spin qubits are much faster in terms of driving the qubits. So they are preferred, right? So we chose to work with spin qubits in a CMOS compatible manner on silicon. We have to look at EDSR based control. There are there are other things like ESR based control is also there, but we looked at EDSR control for certain reasons. We are looking at readout, we are looking at upscaling of number of qubits, and then we are looking at what kind of architecture will go with it, cryogenics and packaging. I think the packaging part I'll not cover in this talk at all. So spin qubits, spins are basically natural 2-level system. Spin plus half, minus half, spin plus 3 by half, plus 3 by 2, minus 3 by 2, right? So that kind of spins you can look at. It has a weak coupling to the environment, and these give you the long coherence time. And I've shown you a very simple schematic from this paper where we talk about a source, a drain, and you can see the isolation between dot and source, drain, and gate, everything, right? So this is isolated, and only tunneling can lead a carrier from one of the reservoirs, either source or drain, to the dot, controlled by the gate potential. So this the at the most basic level quantum dot represented by a disk. Of course, things have advanced much more. This paper dates back to 2007. So why we want to make quantum dots on silicon? You can isotopically purify the silicon to get rid of the nuclear spins, and then it is very, very close to CMOS fabrication, which is where we have a lot of advantage and great learning and expertise across the globe. So you don't want to move away from CMOS technology. Also for the reason that it gives you very high density, so you can actually pack lots of qubits in a small area. And since we are doing CMOS at an industrial scale for 70 plus years, there is industrial scalability always wherever CMOS goes. And you can see different kind of qubit papers across the years. Original proposal coming at somewhere 98, then to 2014, you can see single qubit gates. And now people are talking about very, very advanced qubits, right? So instead of single qubits, we are now talking about multiple qubits integrated in a form of a tile, surface codes and things like that. Couple of those things I will also cover. So this is something that every 6 months you have like a breakthrough, and you have a new design that becomes very popular suddenly. So why we want to work with whole spins? There are few reasons, not too many. So electrons have a weak spin orbit coupling. It has to do with the band structure of silicon, right? Whereas strong spin orbit coupling SOC is observed for holes. So now what happens is the spin orbit coupling is what gives the local gradient in the magnetic field, which is required to operate spin qubits. So if your spin orbit coupling is weak, you have to provide the local gradient in magnetic field using what is called as micromagnets. So for every qubit, you have to create small magnets on top of the qubit, which of course is not CMOS compatible process, and it complicates the process more. So we want to stay away from that. We want to make simple qubits. So we prefer to go with the hole-based qubits because of the strong spin orbit coupling. And this actually results in the control trade-offs eventually when we are doing things like EDSR and so on. So it is important to take that decision. But just to know, since the silicon band structure is in front of us, just you should see that there are heavy hole and light hole bands in the valence band of silicon, which is where holes live, right? So even hole spin qubits will again have specifications with respect to heavy hole and light hole bands. So now if you look at the quantum dot confinement, we're talking about electrostatic confinement, meaning you apply the voltage at the gate, and electric field does the rest of the job for you. So it basically creates, you can create a Coulomb blockade, and then you can allow a single electron to tunnel into a quantum dot. And so now what you see here is, a single electron is tunneled into this quantum dot, a single electron is tunneled into this quantum dot, and there is a barrier between these two quantum dots, which is what the exchange term would be, right? So now you will first have to create a two-state system here in both of these dots, right? And then the barrier will do the exchange coupling, right? So you want to look at the layout. The layout for the not same but similar kind of a device would look in principle something like this. Okay. So why this actually matters? So in silicon valence band, as I said, you have heavy holes which have a effective mass roughly 3 times that of the light holes. So in a quantum dot, you have the confinement and the strain, which will split heavy hole and light hole subbands. So we usually engineer and try to get the heavy hole ground states. And then this is not the pure heavy hole ground state only. There will be some light hole admixture, right? So there is a combination of these two which gives you the best possible results. At the layout level, there are various layouts of qubits which are possible. Intel has by far the most CMOS compatible layout, where they use CMOS-like things like self-aligned gates, very dense routing. They don't use any micromagnets. They use uniform tiles, so there's like a unit cell, and then you can create as many number of qubits as you want in terms of rows and columns. The gate pitches is 35 to 40 nanometers. Is contacted gate pitch, so it's pretty advanced technology, and dot spacing roughly 50 nanometers. So that's what Intel style layout means. And then if you look at the higher levels, in terms of metal stack, the back end of line and front end of line. So silicon is where the channel will be and the quantum dot will be. Above that there is gate oxide, which is the main gate dielectric for your MOS based device. The metal one level you typically route the, so this is kind of barrier gate one level. So this is a 2-gate thing we're talking about. So plunger gates, right, can be there. At a second gate level, you might have barrier gates or accumulation gates, and then at higher metal levels you will have EDSR buses and any readout lines and so on required. Those will be at a higher level. So some of the things that are done by others, such as shared RF buses, local DC tuning, minimal fan out at cryo. So these are the things which, if you are doing a 2-qubit experiment, is probably none of your concern. But if you are, the moment you are trying to make 15, 20, 100 times 100 number of qubits system, all these things actually become limiting and they become the enabler. So it is very important that we design the system correctly if we want to upscale the number of qubits.